Jnanam Paramam Dhyayam. Knowledge is supreme.
We will continue from the last lecture the study of the degrees and leading coefficients of the Hilbert-Samuel polynomial. So, let me recall few. So, we have a local ring, Noetherian local ring M, and using, and Q is a M primary ideal. So, this implies that A by Q is Artinian, and then we consider the graded ring, associated graded ring, which is denoted by GRQA, which is A by Q, Q by Q square, and so on. And this is standard graded A by Q algebra. So, this is generated as A by Q algebra by the residue classes of the generators of XR, where R is where these bars, where X1, X2, XR are elements in Q, and bar denotes image in Xi in Q by Q square. So, it is Noetherian. It is a finite type algebra over an Artinian ring, and then we consider the map, the numerical function from Z to Z, or n, Z plus 2 n, n to n. This was any m going to length over A by Q, Q power m by Q power m plus 1. And for we have proved that for a large m, for large m, this is a polynomial function. This is a polynomial function with rational coefficients in Q. And that polynomial function I am denoting by HQ. This is so because the coefficients are in Q and Q is infinite, this polynomial is uniquely determined, and that polynomial I am denoting by HQ. And not only for the ring A, we have done this for the module. So, we have done, so we have for module M HQM, the notation is at any M, this is length of A by Q as A by Q module, Q power m by Q power m plus 1 m. And for large n, it is a polynomial of degree less equal to number of generators of Q, minimal number of generators of Q minus 1. So, I will denote HQ without loss. I will generate this as a polynomial only, HQM. This is a polynomial with rational coefficients inside. Okay, and then we have also noted that if I take this function for this m, we might have to do with the integers, because no, not for this m, but in general, if you have a finite module or a graded ring, and if you allow some negative grading also, the negative grading, it does not go all the way to all the side to negative side. So, only finitely many negative components can occur. Okay. So, what is PQ? PQM is m is defined by length over A of the module m by q power m plus 1 m. This module is annihilated by power of a primary ideal, therefore, the length is finite. It is a finite length module, and this is for large m polynomial function of degree. Now, degree will increase by 1, because this definition clearly it says that if I take the d of PQ m, this is HQM, where d is a derivative, that means the difference of successive terms. So, what we proved is PQ is a polynomial function of degree less equal to minimal number of generators for Q, and what I was proving, I wanted to prove this lemma, and then I realized that we need Artin-Ries lemma. So, the lemma I was proving was, so this lemma we were proving, if you have exact sequence of 0 m prime to m double prime, this is exact sequence of A modules. Then, and m is the middle one is non-zero. Then, if I take the alternating sum of the functions, so that is, if I take P Q m prime plus P Q m double prime minus PQM, these are the polynomials, and if you take the alternating sum of the corresponding polynomials, then the degree of this is strictly less than the degree of PQ m. So, that means that the leading term of the sum of these two will be equal to the leading term of this. So, they get cancelled and the degree drops. That is what we wanted to prove. And for this, I wanted to use so called Artin-Ries lemma. So, let me recall that Artin-Ries lemma. So, that for that I will little bit more general I will recall. So, I am recalling now. So, we will complete the proof after Artin-Ries lemma. Artin-Ries lemma. So, this can be stated more generally. So, I will state more generally. So, when I say filtered ring, see, like a graded ring has a gradation. So, filtered ring also has a ring with a filtration. So, it is a ring, A with a filtration on A. Now, what is a filtration? Filtration is simply a descending chain of ideals. So, that is a descending chain. It starts with A, whole ring unit ideal A0 contained in A1, contained in An, and so on. Chain of ideals is called a filtration on A. The typical example of a filtration is you just take any A, any ideal, and take the powers of that ideal. So, A power 0 is A, A1 is A power 1 is A, and so on. So, this is a filtration. This filtration is called A-adic filtration. Or filtration given by the ideal. And usually filtration, so it's either you denote it like this, or you denote it simply by F. This is usual notation for a filtration. And for a filtration, you can consider out of filtration you can get a graded ring. So, graded ring associated to a filtration F is, you just take the direct sum. See, these are ideals, so they are abelian subgroups. So, you take the direct sum. So, that is denoted by A prime. This is A naught direct sum, A1 and so on. So, you get a graded ring out of that filtration. So, that is called a graded ring associated to that filtration F. So, there is another graded ring associated to that, that is called, that is usually denoted by GRFA, that is the successive quotients. So, that is A0 by A1 direct sum, A2 by A1 by A2 and so on, direct sum An by An plus 1. This is also this is actually this is called the associated graded ring of the filtration F. So, in particular for this A-adic filtration you get really the associated graded ring with respect to the ideal A. So, GRA, this is A power n by A power n plus 1. And this is a standard graded algebra over the A by ideal A generated by the homogeneous elements of degree 1. Okay, similarly we can do it for the module. So, if you have a module over A, so if M is an A module, filtration on M is a descending filtration on M. This is a descending chain of submodules. So, that is M equal to M0 contained in Mn contained in so on. So, A submodules. Oh, in general, I forgot to mention here, when you say filtration, here filtration should also mean that when I take An times Am, that should be containing A suffix n plus n, so that the multiplication makes sense. So, you see, if sorry, I forgot to mention this. A filtration means a descending chain of ideals with this property. An times Am is contained in An plus n. This will make this ring A prime as a graded ring, because when you want to multiply the elements, you get in the next component. So, such a filtration, the filtration on M is a descending chain of submodules, and you call it, and given an ideal A, we say that this filtration is A compatible or A stable or A compatible if A times Mn is contained in M suffix n plus 1 for all n in n. Then you call it A stable. A filtration on the module is a descending chain of submodules. For a given ideal A, you call it A stable or A compatible if A times Mn is contained in the next one, and you call it adic if this becomes equality for large n, for large n. That means this becomes equality for all n bigger equal to after some stage n naught. So, there exists n naught such that for all n bigger equal to n naught, this equality happens for all. This is called a adic filtration, and of course compatible. So, adic means this condition and A stable. So, that is adic. So, the typical example is if you take the ideal A and the powers of that ideal. So, typical example is if you have an ideal A, ideal in this, and M is a module, then A times n M, this is adic filtration on M. Okay, now first let me write it as a lemma. So, lemma, this is about when the module is finitely generated, the filtered, the graded module. So, we have, remember, we have A prime as, so let me write state clearly. So, A is an ideal in A, M is an A module, and Mn is A compatible filtration or A stable filtration, and let us assume all these of finite submodules Mn's, all Mn's are finite modules, and then we form this graded ring A prime, which is direct sum A power n, and we form the module M prime, which is direct sum of Mn's. So, this is a graded ring and this is a graded module over A prime. So, M prime is a graded A prime module, that is because the filtration is compatible. Okay. then the following are equivalent. Then the following are equivalent. Number 1, the filtration is adic, and 2, M prime is a finite A prime model. So it gives you a criterion to check when this M prime is a finite module over A prime. Okay. So proof is very simple. So you have already noted that M prime is a graded A prime module. So let us indicate the proof of 1 implies 2. So we have given that the filtration is adic, and we want to check that it is a finite module. So filtration is adic. So for large n plus 1 equal to A times Mn for all n bigger equal to some stage n naught. That is given. That is the meaning of it's a adic filtration. So obviously, if I look at M0 direct sum M1 up to direct sum Mn, these MIs are finite modules over A. So this is finite. So this set, the generators here, etc., this is finitely finite over. So this set will generate M prime over A prime, because the later homogeneous elements will come from here, and the coefficients are in ideal A. So therefore later part will be generated by this part. So in particular it is finite A prime module. What I am saying is, you take the homogeneous components of degree 0, degree 1, degree n all together, put it all together, they are generating sets, and it is obvious that all later components will be generated by the earlier one. So 2 implies 1. Suppose it is finite module, then it is finitely generated over A prime. Because it is a graded module, I can assume the generating set is homogeneous element. So suppose that x1 to xr are homogeneous elements of degrees n1 to nr, and we generate M prime as A prime module, and let us take n naught to be the maximum of all these guys, maximum of all the degrees n1 to nr. Then we claim we should check that that stage onwards this equality, the equality. So we should check now Mn plus 1 equal to A n A times Mn. That is the meaning of that it is adic for all n bigger equal to n naught. So let us check this. So note that if I take n bigger equal to n naught, look at this set, look at this m prime n plus 1. This one is precisely all, because these x1 to xr generate, therefore this is precisely the finite sums from I equal to 1 to r, combination of a linear combination of this x1 to xr there. So, ai xi, where ai is actually I can assume by comparing the homogeneous components of degree n plus 1, I will assume that these ai's are actually in a prime n plus 1 minus ni, which is a power n plus 1 minus ni. This is obviously equal to a times m prime n, since this a prime n plus 1 minus ni, which is equal to a n plus 1 minus ni, which is a times a power n minus ni. That proves that the filtration is adic. So, now let us come to the, so when you want to check some filtration is adic, you have to check that the graded module is finitely generated.